So, welcome to the first part of today's. Yes, sir. We are recording. So, I asked Martin. So, I'm the other Martin, you know. We have Martin for the theory and the Martin for the practical stuff. And I asked if I should show some videos, and he said no. So, I put this on the first slide. So I forced the student to build our institute's logo in computer-aided design somehow and give me an STL to run a simulation. So, you know, stupid stuff, but looks nice. So we want to talk today about VirtualFluids GPU, but before we start, I saw that 18 years was wrong. Yeah, what is VirtualFluids? So I learned on Monday, nobody knows, so maybe we spend 5 minutes about it. We have a research code implemented since 2001 minimum, because Manfred Kraftschick brought us to Braunschweig, right? We don't know when it started, not really. But in 2001, Sören Freudiger, aka Textor, and Geller. Sebastian Geller. So they are not at our institute anymore, but I guess Martin goes on a walk from time to time with Sebastian Geller. They started to really implement VirtualFluids in C++, and I guess they restarted it 5 years later because we found out everything was wrong. So, you know, the research, yeah? So first, VirtualFluids was a list-based code or node-based code, and then they found out, okay, this is not scalable on CPUs for, I don't know, several thousands of CPUs. So they re-implemented everything in a block-style code, like we have it today. And so we have a lot more functionality in the CPU code because there's a lot more manpower going into it. I tried to count it, so we have around about 27 students, PhD students or postdocs working on this code. And since 2006, we are playing around with GPUs. I guess until I arrived in 2009, only for some fast papers and so on. And then I was the guy who tried to implement all this stuff into VirtualFluids, this GPU stuff. So always blame me, please. Yeah? There were other guys, but they do everything right. The wrong stuff comes from me. So back in the days, we thought a lot about maybe earn some money with this code or whatever, and nothing worked out properly. We let other guys use VirtualFluids and they have no idea how to use it, then write a paper and say this doesn't work well. And Manfred decided we never give this code to anybody else for several years. And I guess in 2021, roundabout, we can convince him to put everything open source and build up a community and let the people use the stuff. And we need around about 2 years to clean up the code. Yeah, so you know, when you have a PhD student, you just want your PhD. You don't care about a good code style, variable names that somebody can read or understand or whatever. Yeah? You just hack down what you need, and when it runs, you never touch it again, write your thesis and run away. The next guy who's coming said, I cannot do anything with this, throws it away and do everything from scratch again. Yeah, so this was the same in our institute for years. And we said, okay, this cannot go on forever in this style. And we said, okay, we have to invest some time, so I guess around about 2 years, to think about what is good, what is not so good. We learned a lot about what we are doing the last couple of years, because let's say Konstantin and me, we are sitting together over a decade, but in these 2 years I learned a lot of stuff that he's doing I never saw or recognized. Yeah. So in the end, 2023, we published VirtualFluids. And to be honest, it's a subset of all the stuff we have done in the past. Because we cannot clean up everything, it was too much, but we want to finish this thing. You know, there must be a point where you said, okay, now we publish something. So there's a lot of more functionality out there. So this is really hard to read or to understand. And step by step, we try to put in all the stuff in a cleaner and readable version. So it's published under GPL 3 or newer. This means you can use it for your publications, but you have to cite us. Okay? And how you can cite us, this is published on Zenodo, so you can get a DOI for your code if you publish it on Zenodo. And we learned with the last papers that the reviewers nowadays want to have the code on top of the paper to see if what you propose or what you say that you have done in the paper is true. Yeah, they want to check. And this is possible with VirtualFluids. So if you have some new stuff, maybe just a new app, yeah, so you have a convergence study to show something and you build a new app for it, and you say, okay, I wrote a paper and want to publish it, it's in the review process, then they say, okay, I want to code. Then you clean it up, take care of the pipelines, I will talk later about it, and do a merge request. And then if it's CPU code, I guess Konstantin will look into it and check it if it's okay. If it's a GPU code, I will check it. And if it's okay, we will put it in the open source code and do a new release, maybe a minor release, whatever. Because for every release you do, you will get a new DOI that you can cite. Yeah, you can refer to. And this is a nice thing. So this is the base DOI for the first publication of VirtualFluids, but you get for every release, you get a new DOI. So we can directly refer to your version, what you have done, yeah, if you want to publish something. Okay, so I guess I can skip a little bit of this because in the last couple of hours you read this thing, I guess. So we have a documentation, and we learned today again, it's not perfect, but we try our best to improve this stuff. So if you found something that is missing or found something that is wrong, please contact us, maybe by mail, not too complicated, and we try to fix it as soon as possible. This site should help the guys who want to use VirtualFluids and not to make them cry. So if there's something wrong or not helpful, we try to fix it step by step. But you found a lot of stuff here. So the basic introduction, documentation, you found all the modules we have, the namespaces if you want to implement something, which classes do we have, so you see which functionality VirtualFluids provides you, what files we have, and so on and so on. So, yeah, and the easiest stuff to do, okay, we saw today was not too easy when you try to install Docker, but let's say Docker works properly, then you just check out this open source code. Everybody should be able to access this code without any authentication or something like that, and check out to a local copy and then work with it. Yeah, you see you can do it with this variant Hussein showed earlier, but okay, find the way that you are comfortable with. So what do we have here? We just don't only have this open source code. We work in a different way. So if you are a developer or you have to, you want to build something new on top of the provided stuff for your PhD, because you said, okay, I need a different functionality or additional functionality, then you use or you implement everything in your fork. We have several forks right now. So I go through it. So the first fork is the one of Konstantin. And Hussein, I guess, you two work on this fork. Here is main implementation for the CPU code. Yeah, we're done here. Here is, let's say, my fork, but there also Anna Wellman work on it. She cannot be here this week, but she sent some greetings. We two work mainly on this fork. Then we have the fork of Sören Peters. This is the guy who teaches us a lot about sustainability of software and this GitLab CI and so on, what we're talking about in a minute. Sadly, he left us to earn big money at Siemens, I guess. So we will see if this fork will survive for a long time. Then our beloved colleagues from Uppsala have their own fork. There's a lot of additional implementation on this fork, and I guess we will continue with this. So Henry is now a friend because he always helps me to implement something. And we have a fork of Zurich. I don't know if someone is still working on it. This was. I
think they are not. Okay, so they are a little bit more theoreticians. They are not.
I guess this is the old one from.
Or is this from another different group?
No, from back in the days. I don't know his name. Huh? Nee, Oliver's the new guy, the old guy.
Who was the old guy?
When they were in Braunschweig back then. Ich weiß nicht, irgendwas mit.
Zibi?
Yeah, Zibi. I guess this is a fork of Zibi.
Oh.
So this is maybe pretty old. So yeah, once you're in, you never come out. So, but okay, this is if you are here and said, okay, I want to implement something and I don't like this Uppsala guy, for example. Yeah? Then you come to me and said, I want my own fork. Yeah, we can do this. Yeah, maybe some of you asked me at the end of last week to get an account, because for this you need an account. And that's not only depend on me, I have to ask our Gauss IT Zentrum that you are allowed to come in to our GitLab. And when they allow you to come in, then I can put you in this fork. Yeah, this is the thing I can do for you, but I have to wait for the answer. So I create a new ticket on, I don't know, Wednesday or Thursday or something, and I don't get feedback until now. So I'm sorry, but this will come hopefully this week. Okay, and when you work on your fork, basically it works the way that you get the newest version of our open source version. So you pull all new changes, because we have several guys, several forks, working on the same project. So it can be that every day someone is merging some new stuff in the open source code. So this is a living thing. Yeah? This is changing every week, I guess. So when you come to work in the morning, the first thing you should do, you should pull new changes. If there's something new on our base repo, in your local copy, and then work on it. And if you implement something new, then push it to your fork. And when you think it's finished, it's good looking and whatever, then you can create a merge request to open source, and then I will see it, hopefully, or Konstantin or somebody else, and then we will look into it. And I guess the first time we try it, we have some comments about it, to change something and clean up something and so on, but maybe 1 or 2 steps later we can merge the stuff. Yeah, and this is how everybody works right now, and hopefully some of you in the future, and we putting everything in this open source step by step. Yeah, so on your fork you can play around with things. Yeah, everything could be totally crappy and broken and whatever. It's okay. You cannot do something bad to the other guys until you created the merge request. Yeah, this is a step where you can hurt somebody. So most of the time I do it a way that I try something out in my fork and find out this is stupid or this is a good idea, and then maybe make a new branch or something like that where I only put in the nice stuff and then make a merge request for this branch. Yeah, and leave everything out which is grab. Okay, one thing you have to fulfill before I can accept your merge request. Your code has to go through this pipeline without failure. Yeah, this is a really helpful thing, and this is based on the work on Sören. So we have 4 areas that are tested. First, we test if all our compilers compile the code. Yeah, so we check the CLang, GCC for Microsoft, MSVC, and also a GCC for Python. I guess for the Python bindings we need this. So this is the first thing you can crash. Yeah, so we all implemented everything on GCC maybe, and something you implement doesn't work with CLang or Clang. I don't know how to spell it. Then it will crash here, and you have to fix it. I will not look into your merge request. Yeah, okay. When this building works, then we have a lot of tests that should not fail. So we have some unit tests, so I will not tell too much about unit testing, because I'm more a fan of this regression tests. Regression test is something that you should create if you build a new app. So what does a regression test do? He run on our, so we have some, I call it CI pipeline runners. We run your app, create results, and compare the results to older results that we store somewhere else. Yeah, so you once run your application and say, okay, these results are right. Then we store these results. And every time we get a new merge request or something, implement something new, and we run this CI pipeline, then we check if this app still works. Every time. Why we are doing this? I guess around about 10 years ago, we implement something and next day something else. And at one point, we tried out something that we know works the last time we use it. And it crashes, and we don't know why. We have no idea. And then we go back in our history of Git. So last week, we implement only this thing. That cannot be the problem. And go back, and go back, and go back. So we invest maybe 2 or 3 days until we found the point 4 months ago where we implement something that works for the test case we used back then, but not for the test we want to use now. We don't see the problem back then. Why? Because we never run all our apps every time we implement one line of code. Nobody wants to do this. This is crazy. Yeah? But we have machines who can do this crazy stuff for us. Yeah? So every night, this pipeline runs. And if not, I get an email and I have to check why. Yeah, so every night it runs for the open source code.
Also every push by any of the user.
If you push something, it runs for your fork. But every night it runs for the open source version. And every week, but this now runs, fails since 2 weeks. Every week we have an addition regression test for HPC tests, which runs on several GPUs. But I guess the reason is that our cluster is so old that it doesn't work properly in the moment. I have to talk to the admins there. So we have some tests that need a lot more time because we have to start it differently and send it to our cluster, run it there, get back the results, and then check the results. But this in the moment doesn't work, and this is a test that only is triggered once a week. All the other tests are triggered every night. So I always can say, okay, at this night the code does work, today it doesn't work. In between, there have been done something by someone which breaks the code. And this is a nice thing because you don't have to search over months of implementing for finding these bugs. Hopefully. So this is why we do continuous integration. Yeah, so Hussein explained what it is, and I try to convince you that it's a good thing. So we have some analyzer. So we are really, really bad guys. We treat warnings like errors. So Henry know what I'm saying. So you always, when you implement something and you get a warning, you ignore. So it's human behavior, yeah? So I would ignore too, but the pipeline will not ignore. You have to take care of your warning. So if you want the pipeline to pass, yeah? So this is, yeah. And in the end, we always generate a documentation with Doxygen. So we always try to convince you to document your code. Yeah, so how you have to document it for Doxygen, there's an, in the documentation you found something about it, and then the documentation is generated every night in a new version. So the new version of the code is the same like the documentation version. Yeah? Okay. So this is how a regression test is run. So you always start to trigger it, and then we have a bash file who found the existing files where they are lying, and then comparing after running the regression test. Yeah? So this is a dynamic progress that's working on our GitLab runners, and you don't have to care about it. You just have to take care about creating this regression test, creating these files that we want to take to compare your results. Yeah, and this is the HPC version. So I talked to some of you that you maybe cannot use Docker on an HPC cluster because Docker is so closed in itself. If you want to do a Docker-like image parallel, you should use Singularity. This is maybe the same thing for HPC code. Yeah, and then we run the code on this cluster, and the validation is realized to copy back the stuff to our GitLab runners and take the results we have there and compare it. And we have something like, I don't know, less than 1% that we are allowed to differ, the same. So we think about, maybe Martin don't know it, maybe he does. We think about buying some new hardware for the GitLab runners. And it also means that we buy some new GPUs to put it in. And we have, back in the days that sometimes NVIDIA decided to add differently than before, or multiply differently internally.
Yes, it's the rounding, yeah.
Yeah, the round of errors are sometimes completely different, just by using a different hardware. So I guess, and all the guys who have some regression tests will now cry, we have to run all this regression test new when we have the new GitLab runners, because we need new data to compare with. Okay. Okay.
There's a question.
There's a question, yeah.
Let me ask this.
Yeah.
So like, let's say I or someone like adds a new feature,
Mm-hmm.
and you are saying in the regression test they need to compare this with some results. So it's new, like the results they get is the only results.
So you create the first results where you say these results are correct.
Okay.
You give me the results and I store it.
Okay.
And starting from then you have a regression test.
Who's after?
Yeah, yeah, right. Good question. Another question? Okay. So the publishing. Let's say you have implemented a new app, maybe some additional implementation. Then you can look into the documentation where we wrote it too. You have to implement some tests, maybe unit tests. So I'm a civil engineer, so I always feel hard to implement unit tests. Maybe Konstantin hit me because I say this, but so for me, these regression tests are much more feasible and interesting. Then you try to get your merge request through the Martin filter somehow, yeah. And then I say, okay, great, you have a paper, now we have a working code, this fitting to it. Then we release a new version, maybe a minor release, maybe large release, we will see. And then it's working the way that we mirroring everything which is on GitLab to GitHub. So you will find VirtualFluids on GitHub too, because you need to have it on GitHub to publish it on Zenodo. It's complicated, but okay, we will do it. So when you go on GitLab, you always find the last version. If you go on GitHub or Zenodo, you always find the last release, the last official release. Okay? And then, yeah, you get a DOI that you can refer to in your future, and that can be referenced. Okay, so I try to show it up here again, but maybe this is not a problem. Yes, Rosin said it's our release number now is 0.1.2, and maybe the next one's 0.1.3, I don't know. So we have some new implementations from Henry, and some we do together halfway through it. We have to finish this stuff. Then I guess we have a new release when we finish this, because there's a lot of advection diffusion stuff we implement for the GPU, grid refinement for this stuff, and so on. This was missing till now. So it was missing in a readable way, so to speak. Okay. So I go into basic code structure of VirtualFluids. So if you write your application somehow, at the beginning you decide if you write a CPU or GPU application. And these are libraries. Yeah? Everything in VirtualFluids is a library somehow. And you use all these libraries from your application. Yeah? Starting from there, from your, let's say, main CPP or whatever you call it, and use these libraries. So, for example, use the GPU library, or I would do it. And then this library internally look into this LVM library or parallel library where different stuff is implemented. For example, this LVM library is implemented mostly from Sören. Why we have this LVM library? Because everything here is LVM. Because this CPU VirtualFluids and GPU VirtualFluids live next to each other and don't talk too much, yeah, for several years. And we found out this is stupid in some ways. So we try to unify a lot of things now. So we have now the same kernel, the same cumulant kernel we're working on. We have the same grid refinement that we're using. We don't have everything 2 times. Yeah, so we have 2 different data structures that we learned these days, but we invest some time and some work into it that we unifying the most we can. Yeah, that we don't have too much things twice. For example, what we have to do maybe in the near future is that we have only 1 grid generator. Right now we have 2 grid generators because 2 different data structures coming out in the end. So now here's some basics. Yeah, there's some basic stuff you found in here, and also logger and stuff. So we had, maybe this is a good thing about reducing the code, sorry, because we had something like 4 different timers in our code. Nobody knows why. Everyone found, oh, there's a new timer, let's implement it. and nobody knows which is the right one to use, and we talked a lot about it and throw some of them out, yeah, that we only have all the same timer and such things. So sometimes reducing is not a bad thing. So, and if you use the grid generator of the GPU, then you have some sub modules in it, like utilities. There you found something like a communicator or transformator. You can create some geometries like spheres, boxes, and whatever. And you have some I/O sub-library where you can write your generated grid to test if it's generated properly, or where you can read an SDL or another grid and this stuff. So, and then you have the sub-library grid that uses all this functionality to generating your grid, uniform grid, non-uniform grid, whatever. And in the end, you get this structure of arrays. Yeah, what does it mean? You always have 1D arrays. Everything is stored in 1D arrays because the GPU likes this. And so every population, yeah, is stored in one 1D array for every node. So every node has its index. Yeah, and for node 1, you found the first population, the first array, the second population, second array, and so on and so on. So this is the data structure basically of the GPU. So it's completely the other way around, or nearly the other way around in the CPU, because the CPU hardware like it the other way around. Yeah, so it's a bit different. But nonetheless, we try to find things in the grid generator that can be used by both types of codes. Yeah, we try to unifying these things too in the future, I hope. Okay, then here's an esoteric twist once more. Maybe you don't need it because you understand everything yesterday, but Martin said we will show some slides, and so I make some PowerPoint magic yesterday. So this is how esoteric twists work in the list code. So you have this 1D arrays here, and this is a 1D example when you only have a west, east, and west distribution. So we don't call it anymore this way, but let's say this is plus x, minus x, and the 0, 0, 0 distribution. Then we take the rest term at I, so at our index, the east, which is probably in the plus direction, so this isotwist plus, I would call it. I don't know if I'm allowed, but so we take the east also at I and the west population at I plus 1. Then we have our collision, and then we write it back in a way that we take this east, this east distribution after the collision to the west array at I plus 1, because this place is free. Yeah, you can store something. So the west term goes back to the same place, and the post-collision west term goes to the east array at I. And then we change the pointer and call this thing east and this thing west. And so we have the collision and the streaming in this one step. This is basically how esoteric twist works. And maybe you see why we call it esoteric. We all need some time to understand it. This was Martin's idea, and we all need some time to understand why it's a good idea. You know, this is how we work. He has some crazy ideas, and we implement the stuff. Okay, so in 3D it looks somehow like this. You have your distribution 0, 0, 0, and your neighbors in X, Y, and Z. And we store a lot of distribution here at, locally at our node, but also a lot of different ones at the neighbors. And then we have the collision, and afterwards these distribution go to these neighbors on the other side. Yeah, so they're all changing the position. Yeah, so these pictures are taken from our paper. So we wrote a paper while cleaning up VirtualFluids. We write a VirtualFluids paper, which is under under review for half a year, but maybe we can provide this preprint link.
We have a link to a preprint.
Yeah, so then you can read a little bit about VirtualFluids, so we write down what we think it's interesting.
You can actually add the entire paper into the folder. Right. Yes.
Yeah, so we provide a link to the preprint.
Is currently preparing the folder with all the files, where his files, my files, already in it.
Yeah, where we can get everything. So I steal from our own paper. So and here you can see it. Maybe this is more obvious. I don't know. So if you have a preprocessing plus 0, 0 there, then you have minus 0, 0 after the collision, for example. So the all changes always with the other guy on the other side. Okay, I don't know if I go too deep into this. This is the way the CPU code do it. This is the esoteric split. This is something I still don't get completely why it's organized like this. I think this was.
It's just
Just a test, 12 o'clock.
You're sure? So I guess Sebastian Geller was the inventor of this version.
Yeah.
And we're still using it because it's pretty efficient, yeah, on the CPU.
Yeah, so Sebastian Geller made some different version and
Is this still a test?
This is all recorded here.
okay, I guess this will actually be proof that we had this
Yeah.
meeting.
Yeah. That we were here. So now we have a proof that we were here and don't do this from home. So maybe, and this here is maybe a proof that the esoteric twist you can set up as you wish, as long as you fulfill the basic idea. So you can do everything to plus side like I do here. So everything goes in positive direction, or the neighbors are in positive direction. You can put everything to negative side, yeah, to minus direction, and you can do it somehow.
No, I mean, okay,
No.
there may be some important. The one important thing is that you don't crazily mix up things. So because if you look at the neighborhood, then this is 1 octant of its neighborhood, right? So because we put all of them in one direction, so there would be another 7 of these boxes that you could define in the other directions. So this is why you only need to know your neighbors in a certain way, in a certain direction.
And I have to add that yesterday Martin said we only need 3 neighbors, or only neighbors in positive direction and only stopper in positive direction. This is not completely true because we implement some stuff that separately need the neighbor in negative direction. So I added 1 neighbor in minus XYZ to found every neighbor on the other side too. So I also have stopper on the other side.
Yeah. So.
But this is because of we have some
for example,
finite difference stuff there and something else.
Yeah. So I think we started first when even though there are now no particles in this, but suppose you're dealing with particles or stuff that somehow migrates over the cribs. Yeah. Then you are. I mean, the efficient. If you make things more efficient, then they become always more constrained. Say, yeah. So it is efficient in one way, but then it's more constrained in the other way. So if you want to add something, it may be more complicated. Actually, this works very well already with the grid refinement. So for the grid refinement, we also need only neighbors in a certain direction, because in the grid refinement we use these boxes.
Yeah.
But if you want to have particles and you want to get backwards, then you can also reconstruct all the neighbors when you go in exactly the opposite direction to this thing here. Yeah. So in the one that would be the orange one on the PPP node. Yeah. So if you go in this direction, downwards, you come to one node from which you could reconstruct all the others. So that with one additional link that you have stored, you can get through all the 26 neighbors of this node.
Yeah, so we get diagonal in all directions, and then we can go to every other node again by pointer chasing. So we go from pointer to pointer and found the node we need in this moment. So we also need it for some central finite difference calculations and so on. So then you also need the neighbor on the other side. So it's one additional array. I guess it's okay. We talked a lot about it if we need it, but I guess we do. So, okay, this is also sketched here where which population is stored in pre-collision and post-collision. Okay. Okay. How the calculation in the GPU code is done. Basically, you start a calculation. So we look into the setup before or later. We look into the setup, and then in the end you start the calculation. And what does this calculation internally do? It calls some sub modules. For example, the data structure initializer that initialize our data structure. There are two different possibilities. You can create a new grid with a grid generator, or you can store a grid that you can read it again. So when you have a really complicated grid that maybe needs 20 minutes for generation, maybe for other methods this is no problem. They need maybe days for a grid generation, but for Lattice-Boltzmann this is a long time. And you want to do a convergence study, for example. So you want to run it again and again and again, and you don't want to create all the time the grid new because it's always the same. Then you can store the grid and read in this grid just from a file. So this is decided here. So you have to say if I want to read in or generate the grid. Then we have a preprocessor where we initialize all the populations, the boundary conditions and all this stuff. And afterwards we go into the process part where we run the kernels, so the GPU, Lattice-Boltzmann kernels, cumulant, maybe the grid scaling if we have several grids, and also the boundary conditions if we have some. So you can also have periodic boundary conditions on all sides, and you don't need this. Yeah, so you probably can run the whole code only with the kernel without these guys, but most of the time, I guess, you need both of them. And when you are finished, after, 20 million time steps, then you start the post-processor, which creates some arrays again for the output, maybe some additional post-processor stuff we talk about later maybe, and then create the output files for ParaView that you can look into and be happy because it looks so nice. Okay, so here we have an example of the unification. So for several decades, so to speak, we have the same cumulant kernel for CPU and GPU, and then Sören implemented this LVM module where we have one kernel for both of them. And let's say the most complicated stuff is to manage that you have two different styles of data structure, but using the same method here. And this is done in a nice way. So we now have the same here, K17 compressor Navier-Stokes kernel. We talked a lot about this naming of functions and methods and so on. So if you have an idea to call it differently, no. We need two years to find some kind of naming here. So we decided maybe have a little bit long names for everything, but that you can understand what's in there, hopefully. because we had a lot of different versions, shorter versions, but nobody knows what it is, and so on. Yeah, so, and also Konstantin and me, we are calling this function there, and so we have to implement everything only once. Yeah, because every time you have to implement something twice, you do some errors. Yeah, so redundancy is bad, and we want to avoid it as much as possible. Okay, when we want to use the boundary condition, so maybe I don't go exactly through every line here, but you have your main function, so your app if you want, and at the end of this app you always call the simulation and this run method. So you build up the simulation and then you call run, and run always calls this update grid method. And this update grid method is recursive method that always runs the kernel and everything else for the next finer grid. So if you have, let's say, 2 grid levels, then you call this stuff for the finer grid 2 times, and then go back to your coarser grid and call it once. And if you 1 level more, then you go in the finest grid, call it 4 times, in this time 2 times the middle grid, and then once the coarser, and so on and so on. Because we always have to run the next finer grid level 2 times when we call the coarser grid once, as Martin explained yesterday. And yeah, when we have this update grid, so we have this post-collision, pre-collision stuff, then we call this boundary condition kernel manager. Therein you find all the boundary conditions we implemented so far in a clean way. So we have a lot more boundary condition that we played around with in the years, but not every boundary condition has found its way into the open source code yet, but I guess all the good ones will do. And yeah, so we have a factory. Maybe I don't talk too much about factories and all this stuff, so maybe you have to read a book about it. So we have a colleague, Jannis Linksweiler, he's also one of the contributors to our code, who is really a big fan of this stuff and have a great lecture about it. So if you want, this is also in English, so you can join it in summer semester, right? So scientific software engineering, it's called, I guess. There you can learn all this stuff about how to build software properly. Yeah.
So I think we talked about it yesterday, but as a reminder, so like we are using D3Q27.
Yes.
And what is the 17 in case?
It's a year when we published.
Okay.
This
a
cumulative.
year.
It's always a year. So we have a K15, K17, I guess.
Okay,
There's all.
I was not aware that. Okay, because when there's a K15, you would assume that this is using 50 with 70. Yes. Okay.
I guess we discussed this too. If it's somehow confusing.
No, yeah.
But
you will always confuse somebody.
That's why I asked.
you have no idea. You have no idea how long we discussed this. Yeah, so we are somehow numerical guys, and then we talked a lot about how software should be set it up that somebody can use it and don't feel completely lost. And everything works when you change something on this side and not everything on the other side broke down and these things. Okay, so grid refinement, Martin showed yesterday, so maybe I skip this a little bit. So we have this, maybe something you have to know. Our grid interface has to be minimum 3 coarse nodes and 5 fine nodes wide. This is the price we pay for not interpolating the time or in time. This is what he tries to sketch yesterday. So one line breaks down the next line, and then we do the interpolation. So you always have to be aware of this when you set up whatever you want to simulate. You always need this space for this interface, and we suggest have minimum the same amount of nodes in between 2 interfaces, right? Do we have a minimum amount of nodes in between? So maybe when you go from level 0 to level 10 or something, you have several interfaces and you need a little bit space between. So you should not put the next interface directly here. So maybe give it 5 to 6 nodes at minimum, I guess.
Okay, so this is according to feeling. I mean, for rather common sense than really.
Yeah. So there's no no proof of this. Okay. Okay, and this interpolation stuff is also unified. So you will always find this in the IRMB module. There's the interpolation implemented, and the CPU code and the GPU code use this stuff there. So you have now the same interpolation for both codes. So the same routine, so to speak. Okay, and maybe I just say something about this. If Anna was here, she would tell you something about it because she implemented this stuff. Multi-GPU. I guess some of you are interested in using more than one GPU. How is this is solved in VirtualFluids? We have, for example, 2 GPUs in one PC. I guess this is possible, and then you have some inner nodes, of your flow field. Then you have the boundary nodes, so the last nodes you want to use, and then you have some additional ghost nodes. And what you do, you send the values on your boundary nodes to the ghost nodes of your neighbor, so that they can access each other, and the other way around. So you use these boundary nodes on the other GPU and send it to the ghost nodes here. Yeah, so we add one line or maybe one slice of nodes for the communication. This is the price we have to pay here. Some extra nodes where we can. Sorry, I don't understand.
It's just that when you have you divide the grid into 2 blocks now, right?
No, there's 2 subdomains on one GPU and on the other. These are not. Yeah, you can see it as a block, but it's not the same block as Konstantin uses.
Actually, okay, to be accurate, there is a difference with this doing with blocks or not with blocks. Because if you have blocks, then you have a fixed number of nodes in this block. If you have these freestyle grids, so you can simply add one additional line to it. Yeah, so what you would usually do, and I think this is also the only way it is implemented, is that you get a clear cut that is along like you're not going something strange this way, but you cut somewhere straight, right? So you could say this is like you're using a block, but different from a block code, you're adding an additional line of nodes to that area. Now in blocks, you anyway have to do this all the time, because for blocks have to communicate with each other too. They always have this problem. So the blocks always have a line of ghost nodes.
Yeah.
Yeah.
And then that's defined by the user when constructing the grid, how to shape those blocks, right?
So the user. So what is? I mean, Konstantin is probably going to talk about this tomorrow. So VirtualFluids uses uniform blocks, meaning that all the blocks have the same dimensions, but you can choose X, Y, Z dimensions separately, and then they are all the same.
Yeah.
And you, the ghost nodes, they are automatically there.
Yeah.
So here, in that grid, the ghost nodes have to be added, because usually you don't need ghost nodes.
Yeah.
Yeah.
So,
but this is
so VirtualFluids added these ghost nodes when you say that I want to use to run it on several GPUs.
Okay, so as a user, you don't think about it.
You just define your subdomains and where
You define the cut.
you have to define where's the cut, but the rest is done by VirtualFluids.
And the reason why you have to decide, because the obvious choice would then be, wouldn't it, to make the cut so that you split it in two equal sizes?
Depends on if you have a fine grid,
Yeah, okay, yeah.
because you know the coarse grid always have to wait for the fine grid.
Yeah.
So you always, when you just think about load balancing, you always want the same amount of fine nodes on every GPU. But this is maybe a problem we can talk about several days.
Yeah, this is another can of worms
Yeah,
to open. Yeah?
yeah, box of
Yeah.
Pandora. Yeah. So this is something Konstantin has thought a lot more of
About
So-
this, yeah.
yeah, for the CPU code. So maybe there's a lot more functionality in the CPU code. For-
Just one, probably a stupid question. Multi-GPU, when you say it, is it then, what does it actually, is it two, it's like having two separate computers with each GPU, or is it one node? Or
Whatever.
two GPUs that are linked to
Both is possible. If you have one PC with two GPUs, you can use it. If you have two PCs with each have 4 GPUs, you can use it. So
Maybe abstractly you can talk about distributed memory.
yeah, so maybe yeah, we should. I don't know if we should do a lecture about distributed memory, but
I mean, like to say simply.
so
Is the memory distributed then?
yeah, so we have one memory on one GPU and the other memory on the other GPU, and so it does matter if it's on the same PC or not, because the connection is differently from your speed up. Because if you go over the bus on one PC, it's faster than go over. I don't know what network you have between two PCs. Yeah, so this is
I
probably
think
slow.
maybe to be slow, they can communicate via MPI, and then you don't care where they are.
Yeah.
But I believe, and now you have to correct me, that they can also just talk over the PCI Express.
Yeah, but also with MPI.
Okay, so they are
Yeah.
always using.
Yeah, so I always have one MPI process per GPU.
Maybe the question is they do not access each other's memory directly.
No, they don't access each other's memory directly, but I heard in the coffee break that doesn't matter.
It's not a speed up anymore.
There's no speed up if he does it, because No. because of the overlap, I want to talk in the next slides. So we're skipping something, but okay.
But is it then a bottleneck? Because I often hear that this is one of the challenges when you go, I mean, if you can fit everything into one GPU, that's obviously very
Yeah,
fast.
Yeah.
But you often hear that, or I have heard that it's a challenge because it often gets, if you have a lot of communication and between GPUs, that can.
Yeah, and we have to send a lot of data, and this is what I want to talk the next about. So maybe I have to say, okay, we implement it in a maybe stupid way, but it works. So maybe this is something we will improve in the future. But right now, we don't want to take care of edges, corners, whatever. So what we're doing, we first communicate in X direction, and then we communicate in Y direction, and if you have 3D, afterwards in Z direction. By doing this, you know, this receiving node here is then, is this right? Should be then the sending node here. So this information goes to the diagonals too. But only because we do first the X communications and Y then Z. You know what I mean? And so this is maybe the problem here. These nodes in the middle, or maybe these edges, that first you send something to this node, and afterwards you send it up here. And so this node, or this information comes to this point. So we have to send a lot of data, and we have to send it step by step. So yeah, this is a bottleneck. and this is the work of Anna, and sadly she can show it, but I'll try to. In addition, you have to copy the nodes from your GPU in a buffer. Then you use the buffer, copy it to the host, so your PC memory. Then send it via MPI, whatever, to the other node in your HPC cluster, and then copy it back to the buffer and into your grid. So you do a lot of stuff in every time step, always. So we think about what can we do, because if you say, okay, 2 GPUs get a little bit slower, but 4, okay, you see something, 8, okay, it doesn't look good anymore. We try to hide the communication. How can we hide the communication? First of all, we compute the boundary nodes that we have to send. And then while sending these boundary nodes, we calculate the rest of the nodes. So we separate them. This is what we are doing here. And if you only have 2 GPUs uniform in one direction here, we can really hide everything easily. Maybe if you have several GPUs and grid refinement, maybe you come to a point where it costs a little bit, because you don't only have to separate these nodes from these nodes, but you also have to separate the nodes in the interface, because you can cut through the interface. And then you have to send maybe a line of codes, and you only have a phase of interface you can calculate to hide it. Yeah, this is maybe a problem, that you don't have enough to do to hide everything. Yeah, this maybe, then you come to a point where maybe this doesn't work. But there's also things that it's probably solved in a more clever way in the CPU code. And probably Konstantin will tell a lot about communicators and transistors and all this stuff tomorrow. Transmitters, sorry. Yeah, you know, I have no idea. I have no idea what Konstantin's doing, you see. Because, yeah, so you can optimize these things further. So there's some work to do to optimize it. But this hiding works pretty well if you don't have too much GPUs, right? Okay, so you can use it in a good way. So if you want to use, I don't know, 1,000 GPUs and 10 levels of grid refinement, maybe you see some disadvantage. Okay, so this is not scalable to the absolute maximum. Okay, so I guess we go on to the hands-on. Yeah. So is there a break? Do we have some break here today? So should we start right away, or? So you know, maybe. Do you know where?
Yeah, probably now.
So only question. I can go on. So. But
I mean, it depends on the energy levels, I guess. But probably there will be some sandwiches by now. I don't know.
yeah. So we. So it's up to you. So.
So he has enough muscle.
Okay.
You see, that's really
He's fit. Yeah.
Yeah. You can present a cliffhanger after lunch.
Okay. We do. Okay. I try to have a cliffhanger. Okay. So, get out of the slides. Oh. So I sit down. So I'm sorry, but I cannot.
I was sitting the entire day.
Yeah. So So okay. I have to admit, I have a guilty pleasure. I really, really like Visual Studio without the code. So I'm a Windows user and I like my Visual Studio. And we talked about this workshop in the last weeks, and my colleagues convinced me to use Docker and Visual Studio Code. So I apologize, I don't know all these shortcuts here, but we try to get along with it, okay? So I was able to install Docker and check out the code. So here we are. And yeah, I guess what you all do is build this directory here and call CMake. So I guess you don't need this addition that we have in the documentation with this architecture, because somewhere in the CMake there's defined this 5.2, I guess. Most of the times it doesn't matter. So,
Actually, I think this made some problems when I was in India.
yeah, maybe this made some problems, but not on my machines. I don't know. So
It works
maybe,
on my
yeah, so
machine.
here, CUDA architecture is now 5.2, but, and I know my GPU is a newer, so I do everything on this laptop here. So you can use VirtualFluids GPU on a laptop, but it's heavy and has some energy problems, yeah? But basically you can do this. Yeah, so I don't talk too much about the CPU code, because I have no clue what's in it, and maybe I don't go too far into the code, because we have implemented a lot of stuff and we can talk about a lot of things we have done here. So here you see, here's the grid generator for the CUDA, for the GPU code. So if you want to know what we have in here, you go to the folder source, and then in it you see the GPU library. Yeah, you see all the other libraries. Here's the LBM library, where the unified stuff is in. Yeah, you see we have some Chimera transformation header, yeah, where you get everything. When you don't understand what Martin says to you yesterday, you can look into this stuff. Here it's implemented. I don't know why we have a dummy CPP. What is this? Ah, Sören.
So you can start from here, there's the header in it.
Yeah.
Header is very
So here's the header. If you create some new files, you always have to put in this header, because here is this license stuff.
the pipeline would fail.
Yeah, the pipeline will fail if you not have this header in it. So Sören was really hard. We have to be correct in any way. So we also have here some macroscopic values and whatever, so we can see how you get it here, how we calculate the density here, and the velocity and so these stuff. This is the stuff Martin talked about yesterday, how to add things up. Yeah, so here it should be done in the correct way. You see a lot of braces here and brackets, sorry, and all the stuff here. So, and you see here's the interpolation, unified interpolation, here's unified collision, and so on and so on. Advection diffusion. Yeah. I guess for the turbulent diffusivity we need this central stuff,
No,
right?
this depends on what turbulence model you're using. So we had a whale model where we needed some finite differences, but I think what is it called, the AMC? AMD has nothing to do with the processor, yeah. What
Is this too small? Should I?
Isotopic minimum dissipation.
Wait.
Method that uses
Now?
that actually is able to deal
It's better?
only with the derivatives that we get out of the non-equilibrium.
And that's the QR model.
The QR model.
QR doesn't have a It's just pure QR.
Okay, just QR. Sorry, yeah. So we are not using okay, yeah, this is my confusion. We are not using we are actually not using AMD, right? Because we don't have an anisotropic grid. Yeah. So okay, so the AMD is an improvement on the QR methods for anisotropic grids, but then in lattice Boltzmann we don't use anisotropic grids, so we have no use for that improvement. So we go to the original and use this QR
Model.
method. And in this method, all the derivatives that are required can be computed locally from the non-equilibrium moments. But then there are other turbulence models, like in some whale models, that require some additional gradients that we don't get directly from the non-equilibrium moments, and then we have to calculate them by finite differences. And when we do this, we need this additional neighbor. Yeah?
Yeah. Okay, so I guess it's built in some seconds. Maybe we start with some apps. So we provided some apps for you that you can see what you can do, what functionality we have, and so on and so on. And I like this sphere and channel, for example, because driven cavity is boring. I don't know. So maybe we use this app here. And maybe it's always a good idea to start with some apps that is there. Maybe we have enough time today that we together build a new app. Okay, maybe this is something we look at a goal for today.
Also, there is a lot that can superficially use virtual fluids.
There are a lot of people here that are going remote on a bigger PC and use VirtualFluids GPU. Yes? Yes, so a lot of pros. Yeah. So I'm using this machine locally. I have no idea how to go to another PC. So, okay. So yeah, you see you have a lot of includes. Maybe we can ignore it somehow. Maybe if you really want to know, we can talk about each include here. You see we include here some spheres. So you need, for example, this include to build a sphere from the grid generator, a triangular mesh. We need this to read STLs and so on and so on. So we need this grid factory I showed in the slides. And we need here the simulation, the grid scaling factory, and so on and so on. So, and then you come into your, oh no, we have to start in the main, right? We have to go down to the very end. So here is main. Yeah, you know, you always start in the main function in C++. And what we are doing here, it's not too much. We load this config file. So we basically always have a config file. This is this one here. I don't have so much of options like Hussein has, but maybe it doesn't matter. One thing I found out that this doesn't work because you don't find this. Why? Because I'm in workspace, VirtualFluids, and build. Yeah, as you see down here. I'm here. So when I want to go to this app, so I have to change this here. So I go, opala. I have to go one up, I guess without this. So one step up and then go in apps, GPU, sphere and channel, and then there. But this problem is if you do it or you install it directly, this probably is the right folder or the right path, and for this Docker version it's not. So maybe we cannot, or we haven't found a way to define this in a way that it works every time. Okay, we can try to run it. How do you run it? When you build everything, you go to bin, and here should be a sphere and channel compiled, and we try it.
So you have to compile it again because we just changed it.
I have to, okay, you're completely right. Okay, there are two different ways of using VirtualFluids. I'm the one who always implemented something and changed something, so I'm always work in the main CPP somehow. And then I always have to compile before I see the changes. If you are really, really pushing this code away from you and you just want to do a convergence study or something else, then it's maybe the better way to use this config file. Then you don't have to compile it again, because you can change the config file, run it again with the same compiled code. But okay, you have to look what fits better to your workflow. So I'm always changing everything in this main file. Maybe this is stupid. No, we have to make it again. So you see I have some more cores here. I hope this speed up this thing. And what I also will do, maybe we talk later about it, I'm taking here, so we prepared it. You can use this sphere which is generated from the grid generator, and we don't use this STL at the beginning. So we can change it later, but maybe it's nice to see that. Also, I have to do it again. Okay, yeah. I don't want to tell it too often that I'm stupid. Okay, come on. I thought this was only a Windows thing, that he stands at 99% for several hours, or at 100% before he finishes. You always think, okay, I finished, and then it needs the same time again until you really finish. But it's in Docker the same thing. Saved? Yeah, saved. Okay.
I mean, you can, of course, because this is your C++ file, so I mean, you can just change it such that you read the address for your configuration files as the leading argument, right? That's also what some of these apps are set up to.
Yeah. Okay.
I mean, some people like me like to just put F5, yeah, and then running from the out of the
IDE,
and then I don't need to set up the path on the command line. But if you run it from the command line, you can give it as a command line argument.
Okay. Okay. I don't care. So you see I have some NVIDIA GPU here. So, and I have something like 1.5 giganubs on this laptop. I guess this is fine. So, and then we can use ParaView. And look into the results. So where you find the results, so this is the same issue that Hussein has. You have to go to the folder where your project is stored. Yeah? So in my case, I put it in, okay, I guess you cannot see it. Why it's so... So it's in documents in my case. And I have a Git folder and VirtualFluids Docker folder and so on. And he always, or you have to know that the folder here is a copy of the folder in the Docker container. Yeah, it's not so easy to go into the Docker container and change some files from the outside, because Docker want to be safe and nobody should go into it. But here, the setup is done in a way that we can access this here. But when you write your files, so your results, they will be always in this folder. So it's not too easy to store your files somewhere else on a different hardware, for example. Yeah, different SSD or whatever. So if you use this output, so this you see it here, wait. So if you use this thing here, just the string path output sphere, then he put it in okay, in the build folder and binaries. Nee, bin. See output. Here's output. Okay, in build. And there you find this sphere and channel. And here are the files that I've written. So I'm always confused about this. Okay. So I have to go to this folder, documents. In my case, I don't know where you store your stuff, but I have to go to your project, and then build folder, output, and then you find the stuff you have simulated. Oh, this is the wrong file, sorry. Too fast. Here. Okay. And then when we want to see something, maybe can we do it this way? Okay, yeah, better. We make a slice in that direction, for example. I don't know why I do this wing there. Applied. Now we see that here was a sphere. And then we can choose something we want to see, maybe the velocity in x direction. So we started with 0 or 1. 1. And in the end we have something that flows around, but not too much. So maybe I need a mouse, I guess. Maybe we should run it a little bit longer. So where can we do this? So you see this here. I have a time step out. This is the time step every 10,000 time step I want to write in PDK. So this is data for ParaView. And I end at 10,000. Ich hab eine Maus irgendwo, aber ist egal. Thank you. This is a nice boss, you see? Okay. So maybe we add a 0 here, so we run it for 100,000 time steps instead of 10,000, but we write every 10,000 time step a file so that we can see how this is changing. Oh no. Wait, this is stupid. I have to compile it again. So this is maybe the bad thing about doing everything in the CPP file, that you always have to compile the code.
But it is of course only compiling this.
Yeah, it needs a lot more time for compilation if you compile everything, of course. Yeah. But you see, the last step, building the target, always needs some time.
While you build, can I ask a question?
Yes.
So now I can see this is a very coarse simulation because the cylinder is like.
Yeah.
Is it running to? Is it always stable? If you under resolve something and
Not always.
Say I wanted a high Reynolds number and you don't take care or you don't take care of fulfilling these things. What will you just get a bad solution or is it blowing up?
Yeah, it could be blowing up, of course. So the cumulant helps you a lot with this. If you're using BGK, it's blowing really fast. So cumulant, you have a lot more playground, but yeah, you can bring it to crashing. This is the reason why Henry will tell us something about these models on Friday, I guess.
But
These turbulence models.
They are not really okay. Correct. They are not really for stability reasons.
Sorry, what are you talking about?
The turbulence.
The turbulence models.
So there is some tradition with the Smagorinsky models in letters Bosman, that the Smagorinsky model is often just added so that the simulation does not crash. Yeah? So on top of BGK. So you can make BGK stable when you add a Smagorinsky model. But I think that the stability is the actual stability is not really the issue for which you asked the turbulence model. Or do you correct me?
Well, we see that for the supercores simulations that we run, when we run like atmospheric boundary layers, we need additional viscosity. Basically, we need subgrid viscosity because otherwise you have the viscosity, like the kind of implicit MES that is added to the limiter, for example, is not enough.
So does it crash?
Yeah, it detaches.
Detaches.
So the viscosity is so low that it can be a shock wave in the limiter.
Okay.
So that's why we originally added it. So
Okay.
it's to improve the results.
Yeah, but not just for stability.
Not just for, no. It doesn't. No, it never crashes.
It never crashes.
It never crashes, but you have a huge. That's also not what we're looking for.
I thought it's crashing from the.
In the standard solver, if you don't have, if you try to simulate a atmospheric boundary layer without any accountings of the small under-resolved turbulence,
Yeah.
then we will also, in the standard CFD code, see that the flow would just not feel that there's a wall down there. It would just flow like a very fast flow for it, without any enough, there's simply not enough friction.
Yeah, so like a slip boundary condition. So.
Yeah,
So
Zero viscosity.
it may go to an Euler solution.
Yeah.
Basically, it's like that.
Okay, so now we run.
So you have to reload it.
I guess I had it. Why do I don't have reloaded it? Is it? Wait. Because I have not. I didn't run it. Oh, you see, I have to concentrate more on this stuff here. Okay. Sorry. Yeah, so I don't know. So I guess it's for a laptop not a bad value, 1.5 giganoops. Maybe some guys here have a much bigger GPU and are much faster. Some guy, no, one guy. You're the only guy, right? Okay. Okay. Where can I reload it here?
But you have to go to the first, and then you, right?
I have to go to 0.
No, you don't need to go to 0.
Reload files here, yeah. Okay. So now let's have a look if it's working. Okay. So something is flowing, I guess.
Can you show, before in your, what you showed like the level, or the grid level, can you show the grid lines also?
Grid lines?
So there was, the refinement was set to false here.
Yeah, so it's a uniform grid. So maybe we can show here wireframe. Can you see it, right? Can you see it?
So we actually we wanted, because this was just the teaser, but you could set it to true. And
Step by step.
yeah. And then
I guess it was a hands-on.
So
We start from scratch, right?
Yeah.
So maybe if I have to speed up, you have to tell me. But I just want to do it step by step with you.
I mean, maybe do we want to have the lunch break now and then?
Yeah. So
this
this is a cliffhanger.
no, this is the cliffhanger. We're going to have the grid refinement then later.
Much later.
Yeah. Much later. So,
Yeah. Okay.